Okay, thank you, Samodha, for accepting our invitation to have a talk as the SSC seminar series in Monash University. Dr. Samodha Pallewatta completed her PhD from University of Melbourne in 2023 and was a postdoctoral researcher at the University of Adelaide. Her research focuses on developing novel algorithms and designing software systems for managing microservices in edge and cloud distributed environment, with an emphasis on application, quality of service, and security. Samodha received different awards such as IEEE TCSC Outstanding PhD Thesis Award in 2023 for the technical contributions in her doctoral dissertation. Her work has been published or accepted in leading journals and conferences, including Journal of System and Software, Future Generation Computer Systems, IEEE Transactions on Mobile Computing, and European Conference on Software Architecture. Thank you, Samodha, for accepting our invitation. And yeah, the stage is yours. Thanks.
Thank you, Mohammed, for the introduction, and thank you for having me here as well. In the seminar today, I'll be basically discussing about designing systems for management of microservices in edge and cloud environments, especially focusing on IoT applications. So a little bit about me, as Mohammed mentioned, I completed my PhD from University of Melbourne, and I basically worked on placement of microservices, microservices-based IoT applications within edge and cloud computing environments, which included development of both algorithms and also open source software systems to enable automated dynamic management of microservices. And after completion of PhD, I joined University of Adelaide as a postdoctoral researcher. And during that time as well, my focus was on developing software systems for IoT application management, but especially focusing on security, considering various sensitivity levels of IoT data. I'll start with a small background and a scope of what we covered today. With the rapid popularity of Internet of Things applications, we have this concept, distributed computing paradigm called edge computing, which sort of brings cloud computing resources closer to the end user to support latency critical bandwidth hungry IoT applications. And there's also this tendency of using microservices architecture for IoT application development because of their fast development cycles. And so there's this convergence between Internet of Things, microservices, and also edge computing. But one of the main drawbacks of edge computing is the resource constrained nature of the edge resources. So we have this concept, most of the new research is coming out in this area where we have the concept of federated edge and cloud environments, where we consider a multi-domain environment where edge and cloud resources are provided by various different infrastructure providers in different geographical areas, and they collaborate together to support the resources required for IoT application hosting. When we have such a dynamic and distributed environment, one of the main challenges is automated placement and composition of microservices, because microservices, what we call as microservices, divide applications into different dynamic components, and the management needs to be automated, and it becomes a little complicated than when we have with what we have with monoliths. So to do this process, to support this, we need novel software frameworks to support the management of microservices across such multi-domain cloud and edge computing environments. with extensibility and scalability in mind. So I will go through two of my works which cover this area of research. The first one is a framework called Microfog, which I contributed to development during my PhD. This is basically a software framework that consists of a configurable control plane that executes placement policies to deploy microservices across federated edge and cloud environments. And it works and depends on cloud native technologies that are related to microservices like Docker containers, Kubernetes, and service mesh technologies, which are used to manage these microservices. And I will then move to another work which focuses specifically on integrating security, considering the data security requirements of the IoT applications, and how we developed the architectural framework for this and prototype this work using the Microfog software framework. So I'll start with Microfog, which is available and published in JSS. You can refer to this for more details, but I'll cover the basic architecture and what we do with this one. So as I explained, one of the main challenges with edge computing is that the edge computing resources are distributed and resource constrained. So we have federated edge computing architectures to overcome these resource limitations. But in such environments, we have to have proper methods in place for placement and composition of microservices within such environments in an automated manner to handle the dynamic nature. So in this work, which I'm going to explain next, we are going to discuss, we are going to cover design and implementation of a software framework that utilizes cloud native technologies like Kubernetes and service mesh, specifically Istio in this case, to facilitate distributed placement and composition of microservices in a federated environment. So why we did this work was because we have a couple of edge computing software frameworks that are coming up for application management in edge and cloud. But when we consider microservices, there are limitations in those frameworks. So most of these frameworks do not focus on dynamic composition of microservices across federated environments. And majority of the placements are focused on specific template of microservices instead of having independency of the application level changes. So to overcome this, in our approach, we try to create a scalable and extensible framework for deploying and managing microservices within federated edge and cloud environments. So in this work, I'll explain how we've created a configurable control engine to process application placement requests, and also dynamic deployment architectures for major components of the system. Because when we have a software system operating across various edge and cloud resources, we need to have a scalable deployment architecture that would be fault tolerant as well to support continuous placement of the microservices. And also I will discuss how the practical implementation and prototyping of this framework is done, and a couple of use cases to show how it works. The system model, the fog computing or edge computing architecture that we talk of as a federated edge architecture is shown here, where we have different fog computing or edge computing providers providing infrastructure to host IoT applications. And they are divided geographically and also based on who takes care of these resources or provide these resources. But to overcome the resource limitations of edge resources, they collaborate together and provide services to host the IoT applications. So what we try to do is create a software system that runs on top of these edge and cloud resources to help us place microservices and also ensure that they communicate properly to provide a service to the user. I'll explain a small use case to support this. So we have a smart health monitoring application here, considering of 3 microservices, where microservices have to communicate with each other to support different composite services to the user. So we have 2 services where M1 and M2 microservices communicate and provide a result to the user, and M1 and M3 microservices communicate and do the data processing and provide a result to the user. So in such a case, when we utilize cloud-native technologies like Docker containerization, container orchestration, and service mesh, we have to deploy the application in using these resource definitions available in container orchestrators and service mesh. So I'll first explain what we mean by these container orchestrators and service mesh technologies. Because microservices, the concept of microservices is to have independently deployable components of software. So we have this concept called containerization to enable to package these microservices for independent deployment and scale. So in this work, we focus on Docker as the technology for containerization. And the thing with this is like when we have this freedom of independent deployment and scalability, we have to manage these containers at a scale. So to enable that, we have container orchestrators such as Kubernetes. And Kubernetes mainly help us with orchestration of these containers, but there are areas that are lacking related to load balancing, security, service discovery, which are enhanced by technologies known as service meshes. So in this work, we consider a service mesh called Istio, which enables multi-cluster composition of microservices. So for example, if we have M1 and M3 microservices in 2 different edge or fog computing environments, we can have Istio as the underlying service that abstracts the communication between them. But to enable them, we have to deploy certain resource definitions that match these applications. For example, this deployment shows different Istio services such as virtual service, destination rules, and Kubernetes resource definitions such as pods, services, config maps, roles, and role bindings. So in deploying an application on top of the federated edge cloud environment, we have to deploy these resource definitions along these resource definitions to make sure that our application can properly operate on top of the distributed edge and cloud environment. So with our framework, what we are trying to do is help automate the deployment of these applications along with the Kubernetes and Istio resource definitions. So the framework would support the following features, which are multi-edge, multi-cloud microservice placement and deployment support, and the seamless composition between these microservices, which are distributed across such a hybrid environment. And also, we would support the integration of novel placement algorithms and load balancing policies to improve the QoS of the applications. And they would support heterogeneous cloud-native applications without any application-level changes, which means users can simply develop the IoT application, package it as Docker containers, provide us with the Kubernetes and Istio resource definitions, and the framework would take care of placement and proper composition of the microservices. And the framework is developed with extensibility in mind to integrate new features in the future. And to the intelligent layer of the framework is known as the control engine, which supports different placement modes and different operations because it is deployed on top of a distributed environment. And to support the placement, we need different metadata to be stored as well. So the framework could take care of distributed storage solutions to support this. And what we targeted during this is to have a rapid prototyping support to quickly deploy this on top of distributed environments as well. So I will next go through a bit about the architecture of our framework. So as I explained, we have infrastructure with Kubernetes and Istio installed, which means we can deploy containerized microservices on top of this infrastructure. Microfog would run on top of this infrastructure as a microservice. And the main component of this framework is the control engine, which is the intelligent agent, which receives application placement requests from IoT application developers, and then execute placement logic and handle the deployment of the application in an intelligent manner. So to do that, we have different data sources like metadata store, which consists of application models, QoS requirements of the applications, so they can be used as input to the placement logic executor. And we also have YAML files. What we mean by YAML files are the resource definitions that I mentioned. So it could be Kubernetes service definitions, pod definitions, or Istio resource definitions as well. So basically, control engine use this data, execute placement logic, and automatically configure the YAML files to deploy the microservices in certain edge computing resources and make sure that microservices can communicate together as well. We developed this in an extensible manner so we can plug in different placement logics. Either we can extend control engine to add new placement algorithms, or we have APIs to integrate external placement algorithms into the framework as well. So a little bit about the control engine, which is the main component of Microfog. It basically provides an API for the IoT application providers to submit placement requests. And because we are considering a distributed environment, we can do the placement in multiple modes. Either we can have a centralized mode where all the placement requests are sent to the cloud-based control engine, and it conducts the placement of the application in a central manner, or we can do it in a distributed manner where the placement is carried out independently by each resource cluster. But in case a certain cluster is not able to place the whole application within that cluster, it forwards the application placement request to other clusters for completion of the placement. So in that case, the control engine acts in a distributed manner and collaborate with each other to complete the placement. And we can do the placement in two different modes as well. Either we can do it periodically or in an event-driven manner, where when we receive a placement request, the control engine would process that request as it arrives. And as I said, it supports novel placement algorithm integrations. load balancing policy integrations if we want to change the way the load balancing happens inside the when we have like multiple microservice instances deployed. And we can also have the capability to define placement request forwarding policy. But this is related to the distributed scenario of placement. If we want to forward placement requests to other clusters, what sort of a policy we can use. And so basically the control engine would execute the placement logic and then automate the application deployment by configuring Kubernetes and Istio resources to make sure that the microservices are deployed and they are able to communicate properly. So this is like a basic flow of what we have in the control engine. So as I explained, it basically first loads the metadata related to the placement request of the application. And then as the second step, execute the placement algorithm based on those data, and then deploy Istio and Kubernetes resources by automatically configuring them based on the output of the placement algorithm and also the load balancing policies we have integrated into the control engine. So since the control engine is expected to be deployed on top of a distributed environment consisting of edge and cloud resources, we have different data stores. We have different deployment architectures for the data stores and also for the control engine as well. So we deploy it using Kubernetes and Istio to make sure we can have cross-cluster data access and fault tolerance and replication of the data. Similar approaches followed for control engine as well, where we can deploy the control engine, which is a microservice, across different clusters. They can communicate together, and we can direct placement requests to a certain control engine on a cluster as well. And the framework enables an interaction using REST APIs, 3 main APIs, one for placement request submission, and another one for cluster data querying, which means when a control engine is trying to place the application on top of the edge computing environment, it sort of needs to identify how much data is available, which is done by querying each cluster to see how much data availability is there. And then finally, once the placement algorithm is executed and the configurations for the deployment are generated, the deployment information is transmitted to related clusters or related edge computing and cloud computing nodes to deploy the Kubernetes and Istio resources on top of those nodes. So we have this framework available as a open source software framework with Microfog control engine, which is developed as a Java microservice, and also with all the resource definitions and configurations for Microfog and related components available for fast prototyping of the framework and easy deployment. And to demonstrate how to use this, I'll just show some of the experiments we conducted where we considered a distributed edge or fog and cloud environment with various nodes consisting of different resources. And we submitted we ran Microfog on top of this architecture and submitted the application placement requests into it. And we integrated multiple policies into it as well, where we tried distributed placement approaches or centralized placement approaches. And to play around with it, we have a workload creation application as well, where we can mock different microservices and their communication as well to test the framework. And so this demonstrates some of the use cases of the framework. One being how the data store deployments are happening and the failovers between the data stores and how it supports different Kubernetes distributions such as K8s or K3s, depending on the level of resources available. And also with the deployment of the control engine in distributed and centralized modes or distributed and centralized placement scenarios to show how the placement requests are completed in both scenarios and time differences of these. So I won't go into deeper details into this, but you can refer to the paper for more details on how this happens and what are the performance based on that. And this is a basic scenario which shows how the framework works, where we have submitted the application into the system, into the framework, and it basically provides us with an automated means of deploying everything on top of the distributed clusters and establish the communication between the microservices automatically as well. So the users do not have to worry about deploying each microservice and establishing communication between them, but the framework would take care of this. So based on the placement algorithm integrated, the framework would be able to optimize different QoS resources such as latency, throughput, and make sure that the application is deployed properly across edge and cloud resources. So this work basically created a foundational software framework to be deployed on top of distributed edge and cloud resources so that we can easily deploy applications on top of such an environment. And the process would be automated and abstracted from the IoT application developers. So if I move on to the next one, the previous one was basically a foundational architecture. It basically consists of integration of different placement policies. But in this one, we are trying to think about how to integrate security aspects into this. So in this one, the main focus, like I mentioned earlier, is again, Internet of Things, edge cloud computing, and microservices. But we would focus on the security of IoT data because IoT applications consists of data with different sensitivity levels. So when we have a multi-domain environment, there might be restrictions on where to place each microservice based on the sensitivity level of the data that are being processed by the microservices. So while microservices supports granular security controls by providing segmentation of data between microservices based on their sensitivity, still we need a way to automate the deployment and composition in such a way that the security requirements are not violated. So if we take like a simple application, here we have a UAV path finding application, which consists of let's say we have a video processing, pre-processing, and obstacle detection application, microservices which process sensitive data, whereas there are other microservices which process less sensitive data, like weather data. So in such cases, for M2 and M3 microservices, there might be restrictions on where to place them, in which domain to place them due to their highly sensitive nature. But for weather data, it might not be the case. So considering these kind of security restrictions, we see that there are security constraints on where the microservices are to be deployed, and also how the communication between them are completed. For example, let's say for M2 and M3 cases, it might be we need the microservices within the same region to communicate and not go outside of the region for the data. So in such cases, we need to be careful about how the composition rules are implemented as well. So to do this, in this one, we considered two research questions. One on how to define and integrate such granular security constraints. Here, the concept we bring in is the policy as code, which is part of DevSecOps principles, where we define policies alongside our application for automated policy integration and enforcement. And then we check how to integrate these policies into the decision-making process of microservice placement and their composition. So similar to the earlier scenario, we check how to have our control plane improved to integrate the security policy integrations into the decision-making process in an intelligent manner. We try to create, in this one, we propose an architectural framework integrating the security constraints, and we prototype this using our previous microfog framework. The basic framework requirements are the ability to integrate these policy as code and then use it in the placement process and enforce it during the deployment process using Kubernetes and Istio service resources. In this architecture, we propose three main components, such as for the control plane, including a policy handler, which is a new component, microservice manager, which is similar to Microfog, where we consider different placement approaches, and deployment handler, which is to handle the deployment resources similar to Microfog. And the policy handler is the one that is responsible for integrating the security policies, which are defined as policy as code, into the decision-making process. And Microservice Manager uses the data extracted from the policy handler in the decision-making process to make sure that the security policies are not violated during placement of the applications. So similar to the earlier scenario, we consider a similar architecture with Kubernetes and Istio installed, and we introduce the policy engine and policy as code resources in this scenario to handle the security constraints. So we use a policy engine called Open Policy Agent, which reads policy as code files defined using Rego language and do the evaluation and data exposure using APIs. And these policy definitions are used by our control plane in application placement, scaling, or migration algorithms to make sure the security constraints are met. We have a layered architecture in this one, where we have supporting services that have the data stores similar to Microfog and observability solutions. So the data stores abstract the communication between application metadata, deployment resources, and also in this case, policy as code resources. And similar to Microfog, we have a presentation layer which accepts the placement requests, and the business logic layer, which consists of the control plane and do the intelligent algorithms to generate the placement of the microservices and also configure the deployment resources to deploy them within distributed environment. This is basically the overview of the prototype. So we used our Microfog framework and integrated policy agents on top of it to enable the enforcement of security constraints into the decision process. So in this case, because we designed microfog control plane in an extensible manner, here we are able to integrate new placement algorithms that takes security policies into consideration during the placement of the algorithms as well. So the use case that we used to demonstrate the capability of this architecture was the UAV pathfinding application that I described earlier. And here we show different policy as code definitions created using Rego policy. And these are loaded onto the open policy agent and integrated into Microfog, extended Microfog, to integrate these policy definitions during placement algorithm execution. So we looked into the Kubernetes API output after this execution to see if the placements meet the security definitions, where we have restrictions on placement of different microservices. So we especially looked into where our microservices M2 and M3 are being placed, because they were like the security intensive ones that we had, and their communication was evaluated based on the Kiali view, which showed the communication between the microservices. So from these two, we analyzed how the framework is able to place microservices on certain regions or certain domains, considering the security constraints, and also configure Istio and Kubernetes to make sure that the microservices communication is also adheres to the security constraints that are mentioned in the policy as code. The detailed descriptions of how the evaluations are done and the detailed explanations of these views are also available on the paper, which is available online, and you're welcome to go through it and learn more about it. The framework was specially designed with extensibility and scalability in mind. That's why we used a layered architecture to abstract the policy handler, data service layers, to make sure that we can extend this in future to handle more scenarios. And the scalability was covered with the use of policy agents. So we used OPA, Open Policy Agent, which is an open source policy agent that are designed to handle scalable management of policies across different distributed resources. So we can have policies deployed for different edge and cloud domains as well. So in this work, the main focus was on security of the data processed by each microservice, and how to make sure that the microservice placement and also the communication or composition between the microservices meet the security requirements. And we basically used policy as code concepts to make sure how to integrate the policies into the control plane and dynamically enforce them during the placement of the microservices. So these two works sums up sort of the software system related work I've contributed to, which are related to the placement and management of microservices in distributed edge and cloud environments, and focuses on use of open source technologies like Kubernetes and Istio, and extending them towards the edge computing resources, and the integration with cloud as well. And some of the future work that we can do in this area includes developing scalable architectures to store and use observability related data, to improve placement algorithms, and integrate dynamic microservice scaling and migration approaches to enable continuous management of microservices. And another area related to security is having lightweight security mechanisms to have safe data transmission across clusters. And one of the other future research areas includes the integration of such frameworks into CI/CD pipelines to handle continuous updates of the security policies or QoS requirements that evolve throughout the application development cycles. So this sums up two of the works that I've contributed to in the area of edge cloud computing, microservices, and Internet of Things. And I'm happy to answer any questions if you have any.
Thank you, Samodha, for this interesting talk. So I have several questions, but first let's start with the attendees. Please let me know if you have any questions to raise your questions and for the Samodha, please. Feel free to write in the chat, or if you like, please let me know to allow you to talk. Any questions? Okay, some of the one question that I have is you mentioned regarding the policies, the security policies in the second work. First of all, I think that's very interesting problem that you targeted. So how you define those security policies? I mean, is that something, let's say, what are the assumptions, or I don't know, have you had any data sets for those security policies that you consider in your work?
No, actually, in this scenario, we looked into one of the example IoT applications. I'll go back to. So the application we used here, what we wanted to look into is what are the possible security scenarios that comes up if we have an application that process data with different security levels. So we came up with three types of security scenarios here. The first one is domain-aware microservice placement, which means like depending on the data that's being processed by a microservice, there might be restrictions on where to place them. So we might not want to place it on edge domain that is managed by admin 2, for example, or it might be not possible to place it on a certain region due to data security requirements. So things like that could be restrictions on where to place microservices. And also another thing was where to send the data. So in that case, we identified two scenarios. One, if between the IoT data generation and the first microservice, which is the ingress microservice, we might want to send it to the closest edge data center instead of sending it to other data centers. And another scenario is if it's two microservices that are communicating together, we might want to have them within the same domain or within the same region instead of having data being transmitted between domains or between regions. So those are sort of like locality related ones. So they all map on either into where we place the microservice or how we define the routing rules between the microservices.
Nice. Thank you for the clarification. So based on my understanding, then what you have done is you have abstracted, let's say, some security policies. You don't have exactly, let's say, security policies. You abstracted and classified them, let's say, in some categories somehow. Yes. And
yeah,
then
exactly.
applications. Nice.
Yeah.
Uh, ba Based on I mean the slides that I've seen, it seems to me that also you have done it practically, correct? On drones.
Yeah, so we did it practically with multiple cloud clusters. And the application
Uh-huh.
was sort of a mock application that we created with data coming in and changing the
Yes.
data rates. Yeah.
Yeah, that really makes sense. So it means that the actual drones is not there, correct?
Yeah, actual drones are not there. We sort of
You
simulate the
simulated
scenario.
somehow.
Yeah.
Yes, got it, got it. Thank you so much. Because I had some questions. I wanted to see whether you use those, let's say, Kubernetes, for example, cluster. When you created the Kubernetes cluster, have you considered the drones as
Uh,
some of the, let's say, slave nodes in your cluster
mhm.
or not? But I think no. So you have only clusters. Your
Yeah.
clusters is some instances on cloud and edge devices that you have.
Edge devices. Yeah.
Yeah, thank you. And one more question. Regarding the deployment that you have, what you have considered as edge devices? Do you have any specific edge
Uh,
node or?
So for this one, we sort of simulated the edge environment as well in a private cloud. So we created for the edge, we created multiple nodes with varying resources, but resource constrained ones. But for cloud, we used much higher resource availability in that
Yes.
case.
Yeah.
Yeah.
And have you done any, let's say, have you had any specific considerations for the networking to somehow
Um,
emulate, let's say, edge devices when they are communicating with the cloud nodes or not?
That's a really good question. In this scenario, we didn't, but actually, it would be really good to have such a scenario as well. So in this one, because what we were focusing on sort of the policy integrations, we did not consider the differences between the network. But that would be a really good thing to sort of simulate and see as well.
Yeah. Thank you. Thank you so much for the clarification. And one more last question specifically for you is, I know that recently you are joining to the industry. And could you please let us know, because in the attendees right now, I see some students and also some academics. May I know what do you think? What you have learned from this? I mean, the research that you have done so far, that you believe you can use them in the industry. I mean, in the new position that you have. What are the,
So
let's say, skill set you had in your PhD and postdoc that you can use right now in your new position?
Yeah, so that's a really good question. So one of the things I noticed is one of the sort of the talents that we can gain from PhD that we can transfer to industry is sort of like how we adapt to learning new things. So in working with these system design and prototyping, I had to work with a large number of technologies and learn them quickly and adapt them quickly to make new things. So that comes very useful if you're moving into industry where a lot of new things are being done, a lot of new solutions are being developed. So we can sort of transfer our skills in learning new things quickly into it. That was one of the things, and I found the when we were doing research, if we are doing it in a practical manner, that really helps us to transfer that skills to the industry if we decide to move to industry at some point. So when I worked on these ones, so I had to work on design, prototyping, deployment. So when we cover the full cycle of sort of conceptualizing and actually implementing and using it, so that becomes very helpful if we at any point decide to move to industry. That's sort of my experience so far. Yeah.
And on top of that, first of all, I really appreciate, I mean, sharing your thoughts about that, because I believe that significantly helped the graduates that we have in Monash University. Uh, on top of this question, I mean, as you mentioned, and based on your talk, I saw that you have used many technologies. If
Yeah.
can you somehow let us know what do you think as, let's say, one or two, let's say, technologies that can help our graduates in case they are going to join industry after their studies, or even those graduates who are, let's say, going to pursue PhD studies. But in terms of technologies that you have used, I saw that actually you have used Docker containers, Kubernetes. What do you think, what technologies they need, in your opinion, let's say, are the top two technologies that you used and you believe other graduates as well can use and it's beneficial for them?
So in the distributed computing context, if you're working with things like microservices, which is becoming popular now, it's important to know about containerization, especially with Docker. But the idea is like, if you know the basic concepts, you can go into different technologies later. If you know the basic concepts related to, let's say, containerization, but you worked with Docker, and then Kubernetes. So Docker and Kubernetes comes really handy if you are looking into sort of moving into like scalable microservice management and that kind of distributed computing scenarios. And other important technologies, I think, is more into like observability related technologies are really important too, like things like using Prometheus, Grafana, and how to use those data to optimize the applications, optimize the microservice development and also deployment. So in the context of microservices, I think those things are important technologies to know. But the basic thing from my experience is like it's important to know the concepts related to those things when you learn new technologies, to try to identify the core concepts so you can apply it. Even if the technology changes, you can apply them to learn new technologies rapidly as well.
Thank you so much, Samodha. And I also should appreciate for the wealth of information you provide us. And
Thank you.
definitely that's stemming the practical experiments that you have. I really appreciate it. Just one more time, if there is any questions in the, I mean, from the attendees, please let me know. Otherwise, we can finish this meeting.
And
Any
thank you so
questions?
much for having me today as well.
Oh, that's totally our honor to have you as a speaker here in SSC seminars. Thank you. And
Thank you.
it seems to me that there is no other questions. So thank you, everyone. Thank you, Samudha, and have a
Thank
good day.
you. Have a good day. Bye.